To talk a little bit of an overview of generally what's happening in the university, a little bit about what's happening in the state and the nation related to forensic science and how we might advance the field, in our case from a textile, fiber and chemistry perspective. So I quite like this image. So it's a bit like you're the body at the scene and they're about to pick a fiber off your head or your body, if you will. This is one of our collaborators. He's a forensic entomologist. So he looks for bugs at crime scenes, Wes Watson, and this is a nationally and internationally renowned forensic anthropologist who's Professor Ann Ross, both at NC State.
Soy chemistry as a fiber was developed way a long time ago by Henry Ford. It died. You know, when the war came along, no one was working on those kind of applications. Then back in the late 90s, well, I guess early 2000s, the Chinese sort of resurrected it. And they now have a commercial soy product that is soy PVA solution, wet spun based. And it is in the marketplace. It's in some of these applications right now. It is also in the nonwovens. I saw it at IDEA 3 years ago, where they're actually using it for wipes and things like that. And what they're saying is some of this we've actually seen in the processes that we're doing. But one, and it's green, it's sustainable. It has the softness of cashmere. It actually does take something that's very thermoplastic and give it a soft feel to it. And we've seen that in all of our work. Perfect ventilation, we haven't gotten that far on. Being the sole botanic protein fiber in the world, I debate that. There are other developments going on. It does in fact have 18 amino acids that are beneficial to us. And they do have some added protection by adding the soy chemistry as they've developed it.
We're going to talk a little bit about our mass spectrometer and what we mean by a Q and a TOF. I'll show you very briefly about how we get the dyes out for forensic purposes, and then we can analyze them by this instrument. We're going to talk about 4 different classes of dyes, and I've got examples of those, and Elaine has more examples that she'll show you. We've done a lot with dispersed dyes. Nearly all of that was done by Ann Crawford. She's now graduated with her master's degree, is out being a productive member of society, as is Samantha Blake. They're both working in chromatography and mass spectrometry at a lab. Acid dyes is what Samantha did. We have a current student who's on a PhD project with David, and she's in the process of measuring direct dyes. We'll show some of hers. And we're going to talk about the most difficult of these dyes because they're stuck pretty tightly, as you know, to cellulose, and those are the reactive dyes. And we have a different way of going about getting those off of the fiber. And this is an undergraduate who graded his final exam last night. He's graduating Saturday, and this is a postdoc that we've had, Malgorzata Simchik, who's worked on the reactive dyes. So
NIJ National Institute of Justice funded project. So the goal of this project is first to enable the identification of dyes in the fiber and also impurities in the fiber without significant destruction of the fiber evidence, because in forensic science you really don't want to sacrifice too much of the fiber trace evidence. And then we are trying to develop a new mass spectrometric database of the dye fibers. And we do this via 2 approaches. The first one is the LC-TOF, which Keith just mentioned, to analyze the extracted dyes. And the second one is the time-of-flight secondary ion mass spectrometry, TOF-SIMS. So with time-of-flight secondary ion mass spectrometry, you can directly analyze the dye without extracting the dye from the dye fiber. And in this way, you really minimize the destruction of the dye fibers.